Maybe just a minute or so.
Okay. Mm-hmm. Okay, let me start then. It's a great pleasure to introduce Dr. Giulia Semeghini, who is one of the star experimentalists in AMO today, working at different aspects of exotic phases. So Dr. Semeghini did her undergraduate and postgraduate work from University of Milan, and then moved on for a PhD in the group of ultra-cold atoms in Florence, where actually she worked on this amazing experiments on Anderson localization on mobility ages and so on. And then for her postdoc in Florence, actually, Professor Misha Lukin's group on this Rydberg tweezer experiments, and in particular this predicted state spin liquids, this first observations, absolutely amazing work on this frustrated spin systems and this RBB-like states. So hopefully that's what we'll hear today. And so over to Professor Semeghini.
Thank you so much. Thank you for the kind introduction and for the invitation. So as explained in my introduction, I will mainly talk about this spin liquid experiment, but I also want to give you a few slides on a more recent result that I think it's very exciting, and it's bringing this platform to a new level in our mind, at least. So let me just get started. I think right now, so the general context of our work in our lab at Harvard is that of quantum science. And I believe it's a very exciting time to be working on these topics, since over the past couple of decades, there have been a number of very impressive and very significant results over several different experimental platforms in this context. And in particular, the platform we're working with is based on programmable arrays of neutral atoms. So this is a new platform in this context, but it's been quite rapidly developing over the past 7 years, let's say. And I think it's already proven its potential, as you've seen in many talks in these days. So with this platform, we do experiments in mainly two fields. The first one is quantum simulation of many-body phases and dynamics, and the second one is quantum information processing with Rydberg atoms. So these are some of the recent results from our lab, and today I want to talk to you a bit more about these two experiments. So the first one is about these topological spin liquids that were mentioned before, and the second one is a new experiment that we recently posted on the archive a couple of months ago, 1.5, where we demonstrate how we can use a dynamically reconfigurable architecture to achieve non-local connectivity throughout our quantum system. So I will first give you an introduction about the platform. I think you've heard a lot about this platform in these days, but let me just recap the main ingredients here. And then I will talk about these two experiments that I just mentioned, and then I will just give you a few outlooks on what I think is interesting for the future of this field. So let's start with the platform. So what we do in our lab is to create these arrays of neutral atoms. And to do that, we start with two-dimensional arrays of optical tweezers, which are simply these tightly focused laser beams that can trap single atoms. So we can create arbitrary geometries with these optical tweezers by using a special light modulator that we focus at the center of our vacuum chamber, where we have this magneto-optical trap of rubidium-87 atoms. So when we shine the tweezers onto the mouth, we start trapping the atoms onto these tweezers. Here we have about 600 tweezers, and we see we have about 50 to 60% filling fraction of these traps. So here, each green dot that you see is a single atom. Of course, what you see here is that we have a random loading. So the question is, can we deterministically fill a subset of these traps such that we have an ordered array? And to do that, we use a second set of tweezers that are this time not static as the one generated by the SLM, but they're movable in the two-dimensional plane. So we can use this second set of tweezers to pick up an atom at a certain position and then move it to a target final trap that was initially empty. So by doing this sorting process, we get to a configuration like this, where you see that these traps are now mostly filled. And here I'm just showing you a few different experimental repetitions where you see that this sorting procedure works pretty well on average. So here we typically have about 99% filling of these target traps here. So the nice thing of this procedure is that it's extremely flexible, and so we can use it to arrange the atoms into different geometries, as you can see in these examples. And again, the example that we used to demonstrate this flexibility was to create this nice video with an atomic Mario that runs and jumps around. So the first key ingredient of this experiment is this ability to generate arrays of atoms in 2 dimensions with programmable geometries, such that for each experiment, depending on the type of physics that we want to study, we can really change the geometry as much as we want. But now, if we want to do some interesting physics with this, we need to have interactions between the atoms. Here, the atoms are typically a few microns away from each other, and so they don't naturally interact. So to have interactions, what we do is to start with the atoms in the ground state, and then we use an optical transition to excite them to a Rydberg state that is simply a highly excited electronic state, where the effective size of the atoms due to this electronic excitation is much larger than the initial size, such that in this state, the atoms interact with each other through strong van der Waals interactions that scale as 1 over the distance to the 6th power. So if we now consider a pair of atoms at a certain distance r, you can see that if the atoms are far enough from each other, and we have this optical transition with Rabi frequency omega, we can excite one or both atoms to the Rydberg state with no problem. But now if we put the atoms closer to each other, the energy of the doubly excited state is shifting up due to these van der Waals interactions. So at these distances, the excitation of both atoms to the Rydberg state is not allowed anymore. So this is what we call the Rydberg blockade effect. That simply tells us that if atoms are within a certain distance from each other, they cannot be simultaneously excited to the Rydberg state. So within a certain distance, there can only be one excitation. And this characteristic distance is given by the so-called blockade radius that is provided by this condition, that the interaction energy is of the same order as the Rabi frequency of the transition. So with this, we have the second element, which is we can also turn on and off strong interactions between the atoms just by turning on and off this optical transition that couples to the Rydberg state. Okay, so the first thing I want to show you is a quick example to show how this very simple effect that is the Rydberg blockade allows us to generate interesting quantum many-body phases. And so as a first example, I want to show you what happens with a simple square lattice. So what we do here, so we arrange the atoms in this lattice, and then we shine lasers onto the atoms such that we can couple the ground with the Rydberg state. And so in this situation, the many-body Hamiltonian that describes the system is the following. So we have a drive term that is proportional to this operator sigma x that couples G with R, and to the Rabi frequency of the transition. Then we have a tuning term where Ni is the occupation at site I of the Rydberg state, and it's proportional to the detuning of the transition, so the detuning of the optical transition from the Rydberg state. And finally, we have the van der Waals interactions. So if we choose the blockade radius, that is something that we can tune in the experiment. If we tune it such that for an atom in the Rydberg state here, its 4 nearest neighbors are all blockaded, we can ask ourselves, what is the many-body ground state of this system when we have a positive detuning for the optical transition? And you can see from this Hamiltonian that to minimize the energy, we would like to maximize the number of Rydberg excitations. provided that we respect this constraint that comes from the blockade. So in this situation, the many-body ground state is the antiferromagnetic state, where the Rydberg excitations are arranged on this checkerboard pattern. And here in this image, which is a real image from the experiment, the Rydberg atoms are marked with these red circles. So this was a simple example to show you how this very simple mechanism that is the Rydberg blockade actually allows us to access interesting, non-trivial many-body phases. And this is something that we studied recently in this paper, where we studied the whole phase diagram for the square lattice and some of its phase transitions, and it's related to another work from the group in Palaiseau that you've heard from in these days, that also studied the same the same phase diagram for the square lattice. So with this, we are now ready to get into the main experiments that I wanted to talk about. And so let's start with the spin liquid. So just to give you a quick introduction, if you're not familiar with spin liquids, what are we talking about? This is a phase of matter that has been predicted about 50 years ago with the first work in the 70s from Philip Anderson. And the system he was considering there was a system of spin one-half particles with antiferromagnetic interactions on a frustrated lattice, like the triangular lattice. And so his proposal there was that due to the frustration in the lattice, you know, the spins don't know exactly how to orient themselves, etc. And so his proposal was that they would pair up and form these entangled pairs, also called dimers, where the state of the pair is a superposition of up, down, and down, up. So all the spins in the system would form these pairs, and you can easily see that there is not a unique solution for the formation of the pairs. There are many, many ways in which they can pair up. And so in his proposal, the many-body ground state of the system would be the macroscopic coherent superposition of all the possible dimer coverings of the lattice, all the possible ways in which the spins could pair up with each other. And this is what he called a resonating valence bond state, where this word resonating indicates the fact that the dimers are not in a fixed orientation, but they can fluctuate among different orientations. And this RVB state is exactly what he referred to as a quantum spin liquid, due to the fact that this is clearly not a solid phase. We don't have an order, a spatial order in the orientation of the spins. So after this first proposal, people have started to look into this phase, and they found that this has an impressively large number of very exciting and peculiar properties. So as I was mentioning, there is no spatial order, but instead this phase is characterized by a topological order. It has long-range quantum entanglement. The type of excitations in the system have anionic statistics. And among the many, I just want to mention the potential application of this phase to implement robust quantum computation schemes. And this is known, for example, from the toric coding model of Kitaev. So for all these reasons, people have been looking into this phase for a very long time, but up to last year, there was no conclusive experimental evidence in any experimental system available. There are some hints that there could be spin liquids in some condensed matter systems, but a very conclusive and direct evidence was still missing. So what happened was that a group of theorists at Harvard started to look into the possibility of creating spin liquids using our Rydberg atom arrays. And they came up with a very brilliant idea that I will show you in a second. So the idea is to place the atoms on a frustrated lattice. As I was mentioning before, this frustration is a key ingredient. And the specific lattice they chose is a so-called ruby lattice, where the atoms are on the links of a Kagome lattice. So as you can see here, so the underlying lines are a Kagome lattice, and you can see that the atom sits at the middle of these links. Now, what you need to do to have a spin liquid is to set the blockade radius such that if you have an atom in the Rydberg state here, its 6 nearest neighbors are blockaded. So when you are in this condition, you have a hard constraint on the maximum density of excitations that you can have in the system, which is 1/4 of the total number of atoms. You can easily see this if you look at each vertex of the Kagome lattice has 4 atoms around it, and only one of them can be excited at the same time. So this constraint on the density allows us to map this system onto a dimer model of the Kagome lattice, where basically each Rydberg atom corresponds to a dimer that connects the 2 neighboring vertices of the lattice. Okay, this is the idea of the mapping. And basically the fact that we have this constraint on the density means that each vertex of the Kagome lattice can be touched by a single dimer. So the dimers cannot touch each other. So when we have exactly 1/4 density, we have a perfect dimer covering, which means we place as much dimers on the lattice that we can, and we have this constraint on the fact that they cannot touch each other. So this mapping is simply tells us that the constraints that we have on the position of the Rydberg excitations are the same as the constraints that you have for the dimers in the dimer model of the Kagome lattice. And it's useful because it was known in the literature that the Kagome dimer model has a spin liquid phase. So this was the first hint that they were up to something good. And when they did the numerical simulations, they found indeed that there is a quantum spin liquid state there in a certain range of parameters that we can see as the macroscopic superposition of all dimer coverings of the lattice. Again, very similar to Anderson's idea. So what they proved in their work was also that this state has D2 topological order. Now, what we do in the experiment is simply the same thing that I showed you for the square lattice. We turn on this coupling to the Rydberg state. We do some state preparation that I will show you in a second, and then we look at the final state. And here you see an example of a typical snapshot that we take at the end of this procedure, where you see that in this case, the Rydberg atoms are marked by these red dimers. And here we can already see 2 things. The first one is that this is a pretty good dimer covering, meaning we're putting there as much dimers as we can. We have just a few defects here and there. Here you see there is no dimer. Again, here there is a vertex that is touched by no dimers, but it's mostly a dimer covering. And the second thing is that we cannot see any obvious spatial order of the dimers, of the excitations. And every time we repeat the experiment, we see something different. Now, how do we actually prepare and how do we characterize this state? So we perform a quasi-adiabatic state preparation, meaning that we slowly turn on the Rabi frequency of the transition omega, and we start with the negative detuning, such that at the beginning, all the atoms are in the ground state. And then we slowly tune the detuning from negative to positive values, such that we can slowly allow for more and more excitations in the system. And we stop at different detuning and we measure the filling fraction, so the density of excitations. And here you see that this grows from negative detuning to positive, and it sort of saturates or slows down around 1/4. So this is the target filling that we were looking for. But at this point, how do we know if this is a spin liquid or not? So the one thing about topological phases is that they cannot be characterized using local observables, but we need to be able to probe correlations at large distances. And in particular, we need to be able to probe topological correlations. So for that, we need to introduce topological string operators that are associated with this type of spin liquids, this Z2 quantum spin liquid, which are very analogous to what you have in the toric code model from Kitaev. In our system, the first string operator that we want to measure is called Z. It's a diagonal string operator, and it measures the parity of dimers along a string that looks like this. So the string needs to cross the bonds of the Kagome lattice, and it measures the parity, which means that every time you cross a dimer, you get a -1. Every time you cross an empty bond, you get a +1. And I told you before, a perfect dimer covering is one where each vertex is touched by exactly one dimer. So you can see that for this smallest closed string, a dimer covering will always give parity -1 because you always cross one and only one dimer. So if we extend this argument, you see that for each larger loop, the expectation value for a perfect dimer covering will always be -1 to the number of vertices enclosed, because for every dimer you get a -1. So this is true only for dimer covering. If you have something that has a different density, you can easily see that you can get, for an experimental repetition, you get +1, for another one, you get -1. So on average, you will always get 0. So we measure this in the experiment, which means that we take our snapshot and then we measure the string operators, which means we draw this string and we measure the parity, and then we move the string around to average over the entire system, and we also average over many experimental repetitions. And this is what we get for these two loops. So here what you see is that at negative detuning, we have a finite expectation value, but this is a trivial result of the fact that here, the density of dimers is very small. As you can see here, the density of excitation is very small. And so when you draw this loop, on average, you typically don't cross any dimers because the lattice is mostly empty. And so on average, you have a positive detuning. You have more +1s than -1s. But here, when we increase the tuning, you see we reach a point where the average is 0. As I was saying before, it's disordered. So every time you get a different expectation value. But then after delta over omega around 2, you can see that this grows again to a finite expectation value. And also interestingly, we notice that the sign for the two loops is different. As I was saying here, we expect to have -1 to the number of vertices. So it's the expectation value we expect is +1 or -1, depending if we have an even or an odd number of vertices inside. And for this loop, we have 6 vertices here and 11 in this case. So you see one is even, the other one is odd, and so the sign is different. Now we measure the same operator Z for loops of different sizes, as I'm showing here. And we see that in this range of the tunings, we have finite expectation values for all these loops that I'm showing here. So with this, we can conclude that we are observing the transition into an approximate dimer phase, where I use the word approximate because, as you can clearly see, we're not getting +1 and -1. We have some finite expectation value, which tells us that we are in a dimer phase, but it's approximate in the sense that we have a finite density of defects. Now, as I was mentioning before, we expect the spin liquid to be a coherent superposition of many different dimer coverings. So we know we're in a dimer phase, but how do we know that it's a coherent superposition and not just simply a single dimer state? So to measure coherence, we need to introduce the second string operator, which is this time an off-diagonal string operator that we call X. And basically what X does is to shuffle the position of the dimers around. So this is how it's defined. And this time the X strings run parallel to the bonds of the Kagome lattice. Now, if you look at the closed X loops, you can see that what it does is to couple dimer coverings into other dimer coverings. So for example, for this example that goes around an hexagon, you can see that, for example, this dimer covering gets mapped into this complementary one, same thing for this one, etc., etc. So this means that if we measure X on closed loops and we find a finite expectation value, this implies that the initial state had a coherent superposition of the dimer coverings that are coupled by that specific loop. Okay, so this measurement is crucial to find if the initial state we're preparing has indeed this coherent superposition. Now, one tricky thing is, how do we measure this experimentally? This is an off-diagonal operator, it's not in the measurement basis. So to do that, we need to do a basis rotation. Here, I don't want to go into details because it will take a little bit of time, but the idea is that measuring X corresponds to measuring Z after a certain quench of the system. So that is what we do. Basically, we need to change the blockade radius during the quench and let the system evolve for a certain specific time. And then we measure Z, and that is the same thing as measuring X on the initial state. We can talk more about that later if you want. So, but that is the idea. So here I'm showing you the results for the measurement of X on these loops that I'm showing here in the inset. And you see again that we have a finite expectation value on a finite range of the tunings that tells us that we have indeed coherence between different dimer coverings in the state we're preparing. So this is all great. So far we demonstrated that we are in a dimer phase by measuring Z loops, and that we have a coherent superposition by measuring X loops. But there is one more thing that we need to check to be sure that this is a spin liquid. And this comes from comparing closed loops with open strings. In particular, because closed loops are the ones that allow us to detect non-trivial topological correlations, whereas open strings allow us to distinguish the spin liquid from nearby trivial phases. And what you can see here, for example, you remember the trivial phase I was mentioning here, where the expectation value was finite just because the density was small. Here you see that we have finite expectation value also for the open strings, but on the relevant dimer phase, the expectation value for the open string goes to 0. And similarly, in this case, you see we have a finite expectation value for the open string, but then this goes to 0. So in the relevant spin liquid phase, we expect finite expectation values for the closed loops, but 0 expectation value for the open strings. So putting together all these measurements, we can identify what is the range of parameters where we are indeed observing a quantum spin liquid state. And you see there is a finite range of the tunings where this is, where all the ingredients are there. And so with this, we can conclude that we are observing the onset of a quantum spin liquid phase. And again, this is a very interesting result because it's the first experiment where we have a direct way to identify the spin liquid phase and be sure that it's there. So once we had this spin liquid, we said, okay, we can actually try to use it to create a topological qubit. So this is what we did. And to have a topological qubit, to have a topological state, you need an array with non-trivial topology. So what we did was to cut a hole in the middle of the array. So here we removed a few atoms such that we create an inner boundary. So we have this sort of 2D donut shape. And when you do that, you generate two distinct topological sectors for the dimer coverings, which means that you have two sectors where the dimer coverings in one sector cannot be transformed in the dimer coverings of the other sector just by doing local trivial operations. To do the transformation, you will always need to have some non-local transformation that involves many dimers, and in particular, it needs to bring the dimers around the hole. So given the two topological sectors, we can define two logical states for the topological qubit. The first one corresponds to the superposition to the spin liquid, that is the superposition of all dimer coverings in one sector, and the one state corresponds to the other sector. Now we can define the logical operators for this, which correspond to where sigma z is the z string that connects the central hole with the outer boundary. And this is a good sigma z because its eigenstates are 0 and 1, the two logical states with eigenvalues plus and minus 1. Whereas we define sigma x as a closed x loop that goes around the hole. And here the eigenstates are the symmetric and antisymmetric superposition of the two logical states. And so what we do in the experiment is to do the same state preparation that I showed you before for the simple array without the hole, and then we measure sigma x and sigma z. So by doing this, we find that in this quantum spin liquid region that we identified before, we have a 0 expectation value for sigma z and a finite expectation value for sigma x, which tells us that the state we're preparing has a finite, even though a little bit small, superposition with the plus state. So these are just the very few first steps towards the creation of a topological qubit. There is a lot more to do to be able to demonstrate that we can encode and manipulate the topological qubit, but here we gave the definitions and we did the first state preparation for one of the logical states. And there was a related work from the Google group in the same number of science as our paper, where they studied something similar. They prepared the toric code states using their superconducting qubits. Now, with this, I want to move to the second experiment that I wanted to mention, where we studied this dynamically reconfigurable architecture. So first of all, what is the idea? The idea is, so the question that this comes from is how can we achieve non-local connectivity and entanglement in our system? And this is a problem that is common to all quantum platforms, I would say, because you typically entangle qubits by using local interactions. And so the question is, how do you entangle qubits that are distant in the quantum platform that you have? And so there have been a few different proposals in this context for different platforms. And so one idea is to have a quantum data bus. So the interactions and so the entanglement is mediated by something else. For example, in a cavity, you have that the atoms interact through the light in the cavity, or shared motional modes for the ions. Or you can have quantum networks where different quantum systems are connected by something that can be light or something like that. Or there was this proposal for this quantum ion CCD where you have some ancilla qubits that transport entanglement through the system and between different data qubits. And now we'll show you how we decided to do this in our system and how it works. So this is well represented by this picture. So we have our array of atoms. And as I mentioned before, we have these movable tweezers. So we typically use that only to do the preparation of the array. But in this case, we use the movable tweezers also after that, once we already started the quantum evolution. So the idea is you can place two atoms close to each other, perform an entangling gate, and then you can pick up one of the atoms using this tweezer and move it somewhere else to entangle it with some distant atom. So as it's shown in this picture here. So to do this in a good way, we need a few things. So the first one is we use the excitation to the Rydberg state to generate entanglement, but then we always map back to a hyperfine qubit. So we use the Rydberg state just to have interactions, but then we always bring the states back to these two hyperfine states. And the good thing about this hyperfine qubit is that it has long coherence times. So we measured a T2 of more than 1.5 seconds. And the other thing is that the atoms in these states don't interact with each other. And so when you move them around, they don't feel each other. So you can do the movement very freely without having to worry about the interactions between them. And then again, as I was saying, we have these tweezers that we can also move in parallel. So we can do many different operations at the same time. And so with this, we demonstrated that we can transport entanglement through the array, and I'm going to show you this in a second. So the first thing we did was to demonstrate that we can transport entanglement without breaking the quantum state. So the first demonstration was to prepare these pairs of atoms to entangle them. So we entangle atoms in each pairs. And then we move the atoms in each pair far away from each other, about 100 microns away from each other. And then we measure the fidelity of the Bell state that we prepared before and after. And here in particular, I'm showing you the measurement for the parity that shows the coherence in the Bell state. And you can see that basically there is no difference between the two measurements, which tells us that coherence is preserved when we transport the atoms over 100 microns away from each other in a few hundred microseconds. That is so much smaller than the T2 time. So this proves that we can do the movement. We can move the atoms apart after creating entanglement without breaking it, without losing coherence. So at this point, we thought, what can we do with this? And in this paper that I mentioned before, that is on the archive, we showed how we can use this to create 1D cluster states, or a sting code in 2D, or a surface code and a toric code in an actual 3D geometry. Here we talk about an actual torus because due to the movement, we can actually close the boundary conditions in both directions. So we demonstrated that this can be used to implement these error correcting codes. But also we did a final demonstration that is more in a quantum simulation sense, where we use this tool of the movable atoms to measure entanglement entropy in a 1D system. So I don't have time to go through all of these, but I just want to show you one example, which is the toric code, which is also related to what I showed you before for the spin liquid. And so here the idea is that what we want to do is similar to what I was showing before. And this is an idea from Sirac and Zoller from about 20 years ago, where the idea was to create entanglement using an ancilla. So the ancilla mediates entanglement between qubits that never directly interact with each other. So for example, this is a scheme for the toric code, where you have an ancilla at the center of each cross here, and you use the ancilla to connect, you put the ancilla close to each of the 4 atoms to create entanglement. And so you perform these 4 entangling gates, and then at the end, you project the ancilla to create the proper state for the toric code. And this is how it works in the experiment. So we want to create the toric code that is shown here in this torus image. And so what we have is a set of data qubits that are fixed in space. So they are in static traps. And then we have ancilla qubits in movable traps that we can move around and close to each of the data qubits. So what you see here in this video that I'm going to show you in a second, every time you see these red circles, it means that we're performing an entangling gate between those 2 atoms. And then we start moving them. So here is the second, third, fourth, fifth, and then we move the atoms up. Let me show you again. So here you can clearly see how we use this movement of the ancilla to bring the ancillas closer to different data qubits and to perform the entangling gate. So the sequence of these operations actually creates the toric code on these stores that I'm showing here. So in the end, we move the atoms up there such that we can shine a laser on one of the 2 groups, such that we can perform readout in different bases. Basically, we use the light shift coming from this laser to perform a basis rotation and then measure the two sets of atoms in different bases. So at this point, I'm just going to show you the results of these measurements. So we could measure the stabilizers for the toric code. And here I'm showing you the expectation values for the X plaquettes and the Z stars that are defined like this. And also, again, since we have this 3D geometry, we can encode 2 logical states here. And here are the expectation values for this, where I'm showing you the raw expectation values and the error corrected one. This is more error detection, meaning that we post-select only on the measurements where we have the proper expectation values for the stabilizers. And so you can see the power of the error correcting code, where you see that these get post-selected on much larger values. So this is, so the purpose of this was mainly to demonstrate what is the potential and the capability that this atom transport can give us. So with this, I'm almost done, and I just want to give you a few outlooks. So so one thing that we would like to introduce for the future, and that could be useful for the spin liquid experiment, for example, is to have local single-site addressing. So everything I showed you today has a homogeneous global coupling of all the atoms to the Rydberg state. But for example, if we wanted to encode and manipulate the topological qubit that I showed you before, we need to be able to not just measure the logical operators, but also implement them on the system such that we can manipulate the topological qubit. And so, for example, we need to apply the sigma z on this string of atoms, or we need to perform braiding of the atoms, as I'm showing in this second, sorry, I missed my, okay, as I'm showing in this second drawing here. So this requires us to have some capability to have local addressing of the atoms. And this is something that we're working on. That is non-trivial because you don't just need a static addressing, but you also need to be able to move these in time and on fast time scales. So this requires some development on the photonic side of this experiment. As I mentioned, we have now this new capability that is this atom transport that really opens up a large number of new architectures that we can test. Another thing would be to have local individual atom, Rydberg excitation on individual atoms. Another thing would be to have a fast atom state detection that would actually allow us to have mid-circuit readout, and so actually perform quantum error correction architectures, not just with post-selection and error detection as I showed before, but actually performing quantum feedback on the system. And then another thing we would like to test is, are these hardware efficient error detection and correction schemes that have been recently proposed in this paper, for example. And finally, something that we think is very interesting is to test hybrid approaches where we combine analog and digital quantum dynamics. So something as we did for the spin liquid and all our quantum simulation experiments, where you have this analog quantum dynamics with this many body state preparation together with these gate-based dynamics that I showed you, for example, for the toric code. And putting these things together could actually give us a lot of new probes, for example, for quantum phases. So all of this together, I think, opens many new directions in the exploration of many body phases and robust quantum computation that we plan to study in the near future. So with this, I just want to show you what happened to our experiment over the past 2 years. So here is us in March 2020, when we were, this is the last day we were able to be in lab before the lockdown. And so we had a few days to manage to put all of our experiment online such that we could control it from home. And we were successful and a bit lucky. So the nice thing about these experiments is that, for example, the spin liquid experiment was all performed from our homes. So we were able to take all this data remotely. And this is us when we finally were able to meet outside in a socially distant way in the summer of that year. And with this, I just want to acknowledge all the people that were involved in these experiments. This is the experimental team. And these are the PIs that are involved in this project. And as you can see, we need the collaboration of a lot of theorists to be able to work on this experiment, especially for the quantum spin liquid. That was a very tricky experiment. And we had the help, in particular, of Ruben, Ryan, and Hannes to really be able to finish and to be successful on that experiment. So with this, I want to thank you, and I'm happy to take any questions.
Hello, thank you, Dr. Semeghini, for this amazing set of results and a beautiful talk. So there's a question, there are a couple of questions in the chat. So Diksha is asking, as you have shown a plot of parity, can you please explain how do you measure or calculate the parity term?
Sure. Okay, let me get back to that slide. I'll take a little bit. Sorry. So there are two parities in the sense that we're measuring here. The first one is the Z parity. So for the Z parity, what we do is what I was showing here. So we just take a snapshot of the atoms. So here we identify what are the atoms in the Rydberg and what are the atoms in the ground state. And so first of all, we map. So the green dots that you see here are atoms in the ground state. The red dimers are atoms in the Rydberg state. Then once we have the snapshot, we can just withdraw virtually one of these strings, and we just measure the. So here we're crossing two dimers, which means that the expectation value for the loop is now +1, because you have -1 times -1. In this case, again, we have 4, so it's +1, etc. So we just average on this, on different location of the string and on different experimental repetitions, and that is how we measure Z. So I hope this answers the first part. The second part is, so we measured the Z parity, but we also measured this X parity. And here it's a little bit more complicated because, again, we cannot measure directly Z. So in that case, we were just we did the state preparation, took a snapshot. Here we need to do this basis rotation. So here the idea, so I don't know if the question was about this or the first part, but let me quickly give you an answer on this one as well. So here what we do, so what the theorists found was that you can do this basis rotation by doing a certain quench time evolution of the system, where basically you reduce the blockade radius such that the atoms only the 3 atoms in the same triangle are blockaded. So you had the 6 nearest neighbors blockaded, and now you reduce RB such that only these are blockaded. And when you do that, you basically perform a basis rotation such that X is transformed into Z. And so what we do in the experiment is we perform the state preparation and then we do the quench. To change RB, we change omega. And in particular, we need to increase omega by a large factor, by a factor of 14, which means that we increase the laser power by a factor of 200, which was one of the trickiest thing in this experiment. And then we take a snapshot at the end of this that now looks a lot like this one. And we measure Z loops that are that correspond to that are the dual of the X loops, and measuring Z on those loops corresponds to measuring X on the original X loops. So it's a little bit complicated, but I hope it's.
And when you do this measurements, the traps are turned off, like the atoms are free falling, or?
So when we do the Rydberg evolution, we turn the traps off because the Rydbergs are not trapped are anti-trapped. So the Rydberg evolution is done with the traps off. Then at the end, when we do the readout, we turn the traps on again, such that we retrap the ground state atoms and we lose the Rydbergs. So the Rydbergs are detected as losses. So in the measurement, they are on.
Yeah, and when you kind of see the signatures of macroscopic superposition, like by measuring this X by rotating, do you know like how long, like what kind of lifetime this macroscopic like superpositions to have? Or?
Yeah, that's a good question. It's pretty short. So we try to measure it. We still need to do more measurements on that, but the lifetime of this state is pretty short, is less than 100 microseconds. Sorry, it's a few hundred nanoseconds. So it's pretty short, and that is something that is one of the things that we need to work on. So first of all, we need to improve the state preparation, so to have a better spin liquid, because as I said, there is a certain density of defects, and it's not insignificant right now. But also we need to get a better coherence such that the spin liquid survives for longer times.
And so when you have this adiabatic ramp up of the frequencies, the Rabi frequency versus quench, these are with respect to excited state lifetime, the usual, or do you actually need to take care of this macroscopic superposition timescales? Like what sets your adiabatic and quench time scales? So like with respect to what time scale?
Yeah, so the time scales for these ramps is set by so what you want to do there is that, so here, this is a cubic sweep such that we go as low as possible when we cross the position of the minimum gap. So we start with the ground state of a certain many-body system, and then we're changing the Hamiltonian. And so at some point we have a minimum of the gap between the ground and the Rydberg state. So we're trying to go as low as possible there. So the time scale there is set by the gap. But at the same time, we cannot go too slow, because otherwise, if the quantum evolution is too long, we lose coherence, because we have other effects like intermediate state scattering, we have a finite temperature, we have vacuum lifetime and all these things. So we cannot go too slow. This is the slowest that we can go without, and this is just empirically optimized. So we try to go, we try to do different time scales, and we saw what was the best for the state preparation.
So there's a question from Umakant that in the dynamically reconfigurable architecture, does the tweezer laser noise affect the coherence time when the number of transport operations are increasing?
Okay, so I don't think we're limited by the tweezer laser noise right now, because that is one of the smallest sources of noise that we have. I think the main thing there is to be able to do the transport without increasing the temperature. And at the same time, we could do even more operations if the initial temperature was lower. So the main thing there is the temperature of the atom. We don't see an effect of the laser noise yet. It could be that when we fix the other major problems, then that comes into place. But so far, no, that's not one of the main issues.
Regarding that, I had a question that, for the entanglement, you showed a visibility, but can you actually look at a entanglement measure like concurrence or something and see whether when you take them 100 micron apart, whether actually the laser fluctuations kind of get entangled with these two of them?
Sorry, you're cutting off a little bit. I missed a few words. Can you repeat again the question?
Can you actually look at with this kind of control? Can you look at an entanglement measure like concurrence instead of just the visibility to see if there is a degradation? Yeah, exactly here. Yeah.
If there is a degradation, so here I'm showing the two-atom parity just because it's a nice thing to see that the constant doesn't change. But we can measure. You can measure the fidelity of the Bell state, for example. So you have a number that is the sum of coherence and the population, and we don't see any change within error bars. So that's the thing that we're seeing, that and here I'm just showing for a single move. We looked at the same thing for many moves, for example, and we see that if we do the movement slow enough, we don't see changes.
Okay.
So for several moves, so a few tens, I think.
Yeah, it's absolutely magic. It looks.
Yeah, and I mean, it was magic to us as well. We just tried it and it worked very, very well, which was very surprising to us as well.
Yeah, it reminds of those Jeff Kimball experiment for decades. He was trying to localize one atom in a cavity, and this is just magic.
Yeah, no, I agree with you. Yeah.
So there's another question from Raghav, and it's about. I have a question about the toric code on a 3D torus. Are you moving the ancilla bit on a 2D plane? And is it the entanglement between the ancilla and the data bits that maps a torus?
Yeah, exactly. So we're moving in the 2D plane, as I wish. So here, maybe it's not obvious that this thing maps to the torus. You need to look a little bit into the different connections to figure out that it's actually the same thing as this. But yes, we're moving in a 2D plane. And I'm saying it's a 3D torus because you see, when we go all the way throughout the array, we're actually closing the boundary conditions on both directions. This is what we do by going up and then all the way to the right. This closes the boundary conditions, even if we're moving on a 2D plane. And yes, you're right. It's the entanglement between the ancilla and the data qubits that maps, this is what I was showing here. The fact that you move the ancilla qubit next to each atom and you perform this sequence of entangling gates exactly maps onto the toric code of the torus.
Yeah, I guess there's no other question in the chat. So if I may ask a little technical question regarding your experimental setup and the atom deflector, the acoustic deflector that you use. So I guess that's one thing where you send a series of RF frequencies to control each of these deflections. So do you, with this closed by frequencies, isn't crosstalk a problem? And do you see any effect of that? It seems to be completely free of that.
So there is a little, when you put a lot of frequencies inside would you want to create a few different tweezers with the same acoustic optical deflector, we do see some interference effects, and we basically need to optimize the phases between the different frequencies, the different RF frequencies, such that they don't interfere with each other destructively, and so that the amplitudes are more or less homogeneous. But yes, there is some effect of that. And that is more and more visible the larger number of traps you have. But there are ways to compensate for that. Yeah.
But basically, for every 256 atom, you have a frequency. Is that right?
So
two frequencies basically for each of them.
So not really, because when we do the arrangement, we do things in parallel, but we never move like the 200 atoms at the same time. We move a few tens maybe at the same time. It's done in steps, but we don't move everything together. So it's not that many. It's a few, but it's not that many. But I think that's certainly something that will come into play when we want to scale to larger numbers. I think there's something that needs to be taken into account.
And when from 60% you go to a 99% filling, like are you limited by like how fast can you do that? Like how long does it take?
So the whole thing takes, let's say, 100 milliseconds. It depends, of course, on the dimension of the array. But the main limitations there are, for example, it takes 20 milliseconds to get the image from the camera, and that is a big limitation. And so that is something that we are trying to work on to reduce the imaging time. And we do it in two steps. So we do a first move, we measure again, we do a second move. So the imaging time is quite a big limit on that time. And the rest is how fast we can move. And again, that could change a little bit if we had deeper traps and better temperatures. And
so that's the heating limitation, is that?
Yeah. So it's heating in the sense that you lose them at some point. We do cooling throughout the whole thing, but if you go too fast, you actually expel the atoms from the traps.
So how did you make the movie actually? Like, is that like many different?
Yeah, the movie is many different. Yeah. Okay. We take many measurements for each. Yeah.
Okay. Yeah, I think there is one comment, but the cameras are of high power. Then how taking that much time? I think like it's trying to say that why it's taking 10 milliseconds.
Yeah. So a part of it is just to collect enough fluorescence, enough photons from the fluorescence imaging. The second part is just how long it takes to transmit the signal from the camera to the computer. And so these are fundamental limitations that, there are faster cameras and we're actually testing those, but there is a limitation that is atomic physics. We don't want to be too close to resonance, otherwise we heat up the atoms. So if you're off resonance, it takes more. So we're working on different levels. We're increasing the numerical aperture such that we can collect more photons. We could work on more closer to resonance imaging, but again, we need higher depths for the tweezers. So there are many factors there, but some is atomic physics. The other part is camera technology.
Okay, so I guess that's all about the questions. So if there are any other questions, someone can just unmute and ask. Or otherwise, yeah, thanks a lot, Giulia, for this absolutely exciting section, really. Yeah,
Can I ask one question?
Yeah, I think Kanaya wants to ask a question. Yeah.
Yeah. So this is very, basic question about Rydberg excitation. For example, if I'm having a terbium atom, I want to do Rydberg excitation. So there are two possibilities. I can go through the singlet state, and then lasers are readily available. One requires 399 nanometer, another requires 395. There is another possibilities which requires, for example, intercombination line 556 nanometer, but the intermediate state line width is 182 kilohertz. But there is another laser which is required like 305 nanometer. Generally, people prefer this 305 nanometer path. except about, the better controllability, easy way of controlling the detuning from the intermediate state. What is the other disadvantage from going from through this 1P1 path?
So, so I'm not sure I got, so let me say a few things and then you tell me if I'm answering. So what we're doing here is we're using an intermediate state. We have 420 and 1013 light to do we do a 2-photon excitation. And that, so the advantage there is that the lasers are available, the lasers that are available at those low wavelengths have high power, etc., and are easier to use than UV lasers. But of course, you have this problem of the intermediate state scattering. And so there, if you want to compensate for this, and have a larger detuning from the intermediate state, you want very high powers for the two steps of the ladder. So there are advantages in going to one single photon excitation you don't have that, but there are a lot of other disadvantages. And so I think it's not completely obvious what is the best path there. I think that there is a matter of commercially available lasers at good powers and that are easy to use. People that are working with UV lasers say that it's very complicated and these lasers need to be maintained a lot and they have a lot of problems. And on the other side, you have some disadvantages on the atomic physics side. But so there is a trade-off between these different things. But I'm not sure if I'm answering your question.
No, you are partially answering the question. So how much this line width of the intermediate state matters?
So it matters because you have this intermediate state scattering. So it depends a lot on the tuning and on the power of your lasers, but you have off-resonance scattering from this intermediate state. So that is a problem, and that is one of the main limitations to the coherence of our system. And so that's why it's not ideal.
So in your particular case, how much detuning is there and how much power you are using?
So we are a few gigahertz away from the intermediate state.
Okay. Thank you very much. That helps me a lot. Okay.
Okay.
Yeah.
Hello.
Yeah.
Yeah, I guess I had a quick one last question, because you mentioned you ramp up your laser intensities to 200 times.
Mm-hmm.
How do you do that without boiling of the atoms? Right.
Without what? Sorry.
Without boiling of the atoms there. Right.
So yeah, that was the tricky part. So so basically, we increase the power of one of the two lasers of the blue laser, not of both, and that allows us to multiply the Rabi frequency by a factor of 14, if I remember correctly. So that is a tricky thing because that's a huge dynamic range for the lasers, and there basically we have a compromise where we use a quite low Rabi frequency during the state preparation, and then we push to a very large one for the measurement and this quench. That is a compromise that we don't love because having a low Rabi frequency during the state preparation means that the state preparation is not great. Because if you have a lower Rabi frequency, you would like to go slower and slower, but we have the coherence effect, so we cannot go too slow. So one of the things that we're thinking of is how can we do this change of the blockade radius without just relying on the change in omega. And there are other ways, for example, to tune the interactions that could be, for example, microwave dressing or things like that. So these are things we're exploring that would make the state preparation and the quench a little bit better.
Thank you. Thanks a lot for this amazing talk. And I would just transfer the thing to the organizers, Professor Bhanudas.
Okay, thank you, Shaikat. And thank you very much, Dr. Semeghini, for a really outstanding talk. And I certainly, I'm very thankful because I know that you got back to Boston. I think last night you were in California for a conference. And thank you so much.
No worries.
Okay, so I'll make some concluding remarks, and then I think Umakant can say a few things. It was about a few months ago that, in one of my discussions with Umakant, we felt that it would be very appropriate to have, this webinar on cold atom quantum simulations and computation, because there's a fairly large cold atoms community in India, but they had not really got into this field. So we thought, it would be very timely. And soon after that, there were these amazing results from, Dr. Semeghini's group. And so we thought, we must go ahead and have this webinar. And I contacted various groups, and fortunately, they were all kind enough to accept our invitation. And so we've had a really, exciting webinar for the last 3 days. And now this was possible because of the help that I got from a lot of people. I mean, I would like to thank the administration of our center, the Center for Quantum Engineering Research and Education, and many of my colleagues at the center helped, in particular Dr. Prasanna, though he was not well. And I would, like to thank Miss Emma from the iHub, the Quantum Technology Hub, for her, from her organizational skills and ability, and she actually did most of the work. And Professor Umakant for overseeing, the efforts we were making. And I certainly would like to, thank all the speakers and all the, the chairs and the audience as well. So I think all in all, it has been a really, an amazing webinar. I mean, I learned a lot myself. And, with these few words, I would like to request, Umakant to say something.
Thank you, Bhanu. So yeah, I mean, as Professor Bhanudas said, this idea of having this webinar is a very timely event in Indian science, because quite a few of us in the country are getting into, they have knowledge about cold atoms and other things, but this new area of quantum simulations using ultra-cold atoms, it's picking up rapidly, and quite a few of the colleagues are here already. And yeah, and I would like to second what Professor Das said just now, that I mean, I personally would like to thank all the speakers and all the chairs, including Professor Saikat Ghosh, who is here now. And yeah, of course, I mean, see, once we floated this idea and started working on it, unfortunately, in the last 1 month or so, things kind of went out of control with respect to the COVID situation at our institute and also at in Kolkata. And in spite of all that, many of our colleagues from the administration, especially Ms. Emma, has been very active and has been helping us with organizing everything related to this webinar. And I mean, I cannot thank her more. And of course, our entire administration, including our director of IISER Pune, has been very cooperative in having this webinar. And because these days, whenever one says a webinar, I mean, I'm sure many people are tired of having many webinars. So we were also reluctant in the beginning. We wanted to have something like this in person, and we were hoping that things would change over time. But then after the conception of the idea and in between, things rapidly change. So we decided to just go with a webinar now. Hopefully in the future, we will have something in person and where we can all interact and have a much more vibrant discussions and interaction time and all that. So yeah, thank you all. Thank you very much for being here and delivering wonderful talks and listening to this entire new vibrant area of quantum science. Yeah, thank you. So we'll see sometime in the future, maybe we can all have an offline conference very soon. Yeah, over to you, Professor Das.
Okay, I mean, so let me thank everyone again and hope to see all of you in the near future. Thank you.
Yeah, thank you all. Bye. Good night, good evening.
Bye-bye.